The year 1921 was a turning point for modern physics, specifically on December 8th when Albert Einstein presented a paper to the Prussian Academy of Sciences that proposed something truly radical. It wasn't written by Einstein himself, but by a relatively unknown mathematician named Theodore Kaluza. This paper, titled On the Unification Problem in Physics, suggested that our universe doesn't just have three dimensions of space and one of time, but a hidden fifth dimension. This wasn't science fiction. It was a rigorous mathematical attempt to solve the greatest puzzle of the era: how to unify gravity with electromagnetism. Today, we're looking at why Kaluza felt forced to ask for help from this extra dimension, and how his condition condiligence laid the groundwork for everything from string theory to our modern understanding of the forces of nature. The year 1921 was a turning point for modern physics, specifically on December 8th when Albert Einstein presented a paper to the Prussian Academy of Sciences that proposed something truly radical. It wasn't written by Einstein himself, but by a relatively unknown mathematician named Theodore Kaluza. This paper, titled On the Unification Problem in Physics, suggested that our universe doesn't just have three dimensions of space and one of time, but a hidden fifth dimension. This wasn't science fiction. It was a rigorous mathematical attempt to solve the greatest puzzle of the era: how to unify gravity with electromagnetism. Today, we're looking at why Kaluza felt forced to ask for help from this extra dimension, and how his condition condiligence laid the groundwork for everything from string theory to our modern understanding of the forces of nature.
It's fascinating because at that moment, physics was at a crossroads. Einstein had already revolutionized our understanding of gravity with general relativity in 1915, showing that gravity isn't a force in the Newtonian sense, but rather the curvature of four-dimensional spacetime. But then you had electromagnetism, described by Maxwell's equations. These two pillars of physics were completely separate. Kaluza's insight was born from a sense of aesthetic frustration. He looked at the math and saw a dualistic nature that he felt didn't do justice to either theory. He wanted one single universal tensor to explain everything.
And that's where the fifth dimension comes in. Kaluza basically says in the paper that if we stay in four dimensions, we've run out of room. There aren't enough mathematical components in a four-dimensional metric tensor to account for the electromagnetic potential. So he makes what he calls the extremely odd decision to add a fifth dimension. But how do you add a whole new dimension without anyone noticing it in their daily lives? We don't see or feel a fifth direction.
That's the brilliance of his cylinder condition. Kaluza assumed that while this fifth dimension exists, physical reality doesn't change as you move along it. Mathematically, he set the derivatives of all field components with respect to this fifth coordinate, which he labeled x0, to vanish. It's called a cylinder condition because it imagines the universe as a cylinder, where the fifth dimension is the circular cross-section. If the circle is small enough, or if nothing changes as you go around it, you only perceive the long, four-dimensional length of the pipe. This allowed him to maintain the four-dimensional variability we actually observe while using the extra mathematical real estate of the fifth dimension to house the electromagnetic field. So, he expands Einstein's gravitational equations into 5 dimensions. When he writes out this new larger metric tensor, what does he actually find? Does the math actually split apart into the two forces he's trying to combine?
It's almost spooky how well it works. When Kaluza writes the vacuum field equations for gravity in 5 dimensions, they naturally decompose. You get the standard 4-dimensional Einstein equations for gravity, and then, emerging from the extra components of the metric, you get Maxwell's equations for electromagnetism. He literally derives the electromagnetic potential from the geometry of spacetime. Specifically, the components that link the fifth dimension to the other 4, the G0 mu terms, behave exactly like the electromagnetic potential. It was a mathematical miracle. Even Einstein, who sat on the paper for 2 years because he was skeptical, eventually wrote to Kaluza saying the idea of unification through a 5-dimensional cylinder world had never occurred to him, and that he liked it at first coffee, though he later had many questions.
But there's a catch, isn't there? Kaluza's paper mentions a corner potential, or a component called G00, that remains a bit of a mystery. In the text, he calls it the yet unexplained G. If you're adding a fifth dimension, you don't just get electromagnetism. You get this extra scalar field. What did he think that was?
That's the sphinx of the theory.
In his original derivation, Kaluza eventually treats it as a constant to make the math fit, but that's a bit of a fudge. Today we call that extra field the radion, or the dilaton. In Kaluza's time, it was a problem because it predicted a field that didn't seem to correspond to anything they were measuring in 1921. He notes that this corner potential is essentially related to the gravitational potential, but he struggles with it. He also faces a massive hurdle when he tries to apply the theory to actual particles like electrons.
Right, he talks about the serious difficulty of the electron. He points out that the ratio of an electron's charge to its mass is enormous. When you plug that into his five-dimensional geodesic equation, the math that describes how a particle moves, the term for the fifth dimension doesn't just contribute a little, it's supposed to overwhelm everything. He says it defies all experience. If the electron is moving through this fifth dimension, why isn't it behaving in a way that's completely alien to our four-dimensional observations?
Exactly. Kaluza's second approximation, which he uses to derive the standard force equations, assumes that the velocity in the fifth dimension is very small. But for an electron, that velocity is basically its charge-to-mass ratio. Since electrons are highly charged and very light, they should be screaming through the fifth dimension at incredible speeds. This threatened to break the whole thing. Kaluza admits in the paper that the theory can only coarsely describe macroscopic phenomena and might fail at the level of elementary particles. He even mentions the sphinx of modern physics, quantum theory, as the ultimate threat to any universal onslaughts like his.
It's interesting that he mentions quantum theory because just a few years later, in 1926, Oscar Klein stepped in to fix some of these issues, which is why we now call it Kaluza-Klein theory. Klein's contribution was to suggest that the fifth dimension isn't just a mathematical convenience with a cylinder condition, but a physical reality that is curled up or compacted into a tiny circle. This explains why we can't see it. It's smaller than an atom. And that compactification actually helps address the quantum nature of charge.
Exactly. Klein showed that if the fifth dimension is a tiny circle, the momentum of a particle in that dimension is quantized. And guess what that quantized momentum looks like to us in four dimensions? It looks like electric charge. So Kaluza's idea that charge is just motion in the fifth dimension became much more robust when you add the quantum perspective. But back in 1921, Kaluza was working with purely classical tools. He was trying to find a fully satisfactory point of view where gravitation is actually a difference effect between other forces. He was essentially looking for a way to show that what we perceive as gravity might just be the leftover bit of a much larger five-dimensional interaction.
He has this very poetic line toward the end where he says it's hard to believe that all these formal relations are just a capricious accident. He's arguing that the mathematical elegance of the five-dimensional model is too beautiful to be wrong. But beauty isn't always truth in physics. Even after Klein's improvements, the theory struggled. It didn't account for the other forces we discovered later, like the strong and weak nuclear forces. If you want to include those using Kaluza's method, you don't just need 5 dimensions, you need 11.
And that is precisely what modern string theory does. It's the direct descendant of Kaluza's 1921 paper. String theorists use extra dimensions, 10 or 11 of them, to unify all the forces of nature in exactly the same way Kaluza tried to unify just 2. They use the same compactification trick that Klein introduced to hide the extra dimensions. Kaluza was the first to realize that the geometry of space could be more complex than what we see, and that this complexity could be the source of the laws of physics themselves. He transformed forces into geometry.
However, we should be careful not to paint Kaluza as a lone genius who got it all right. His paper is full of what he calls full reservations. He knew his cylinder condition was a bit of a hack. He also knew that his treatment of matter as a rest mass density was an approximation that didn't hold up under microscopic restlessness. He was very aware of the epistemological difficulties piled up in front of this theory. He wasn't saying, I have found the truth. He was saying, look at this amazing possibility. It took Einstein years to even agree to publish it because the physical justification for that fifth coordinate was so thin.
True, but Einstein's hesitation is also what makes the eventual publication so significant. Einstein was the gatekeeper of the Annalen der Physik and the Prussian Academy. For him to submit Kaluza's paper meant he saw something deeper than meaningless formalism. Even if Kaluza couldn't explain why the fifth dimension was hidden, the fact that Maxwell's equations popped out of the vacuum Einstein equations was a triumph for the general theory of relativity. It proved that Einstein's geometric approach to physics had more power than even Einstein realized.
It's also worth noting the historical context. In 1921, the physics world was reeling from the success of general relativity's prediction of light bending during the 1919 eclipse. Everyone was looking for the next big thing. Hermann Weyl, who Kaluza mentions in the first paragraph, had tried a different approach using gauge invariance to unify gravity and light. Kaluza explicitly contrasts his work with Weyl's courageous attack. Weyl tried to change the geometry of 4 dimensions. Kaluza decided it was easier to just add a 5th one. History eventually favored Kaluza's approach of adding dimensions over Weyl's approach of changing the metric's fundamental nature, at least in the context of unification.
And yet Weyl's idea of gauge symmetry became central to the standard model of particle physics. So both men were touching different parts of the same elephant. Kaluza's specific contribution was the extra dimension as a repository for physical fields. This idea of higher dimensional space is now one of the most productive tools in theoretical physics. When we talk about M-theory or the holographic principle, we are walking through the door Kaluza opened in 1921. He showed that our 4D world could just be a 4-dimensional part of a larger R5 manifold.
But we still haven't found experimental evidence for that 5th dimension. We've built the Large Hadron Collider. We've looked for Kaluza-Klein towers, which are predicted particles that would come from the harmonics of the 5th dimension. And so far, nothing. The rich physical experience Kaluza mentions at the start of his paper, which he admits provides little suggestion for an extra parameter, still holds true today. We are still in a position where the math is ensnaringly beautiful, but the physical proof is absent.
That is the central tension of modern theoretical physics. We follow the beauty of the math, and it leads us to these incredible structures, but nature's under no obligation to be as complex as our math allows. Kaluza ended his paper with a hope that if it could be proven there was more behind the presumed relations than merely meaningless formalism, it would be a new triumph. 100 years later, we are still trying to prove it's more than formalism. We've built entire careers and multi-billion-dollar experiments on the hunch that Kaluza's capricious accident was actually a glimpse of the true architecture of reality.
It's a reminder that progress in science often comes from these extremely odd decisions. Kaluza was a mathematician in Königsberg, not a high-profile physicist in Berlin or Copenhagen. He sent this idea to Einstein out of the blue. It's a testament to the power of a single, bold idea to reshape how we think about the entire universe. Even if the 5-dimensional model isn't the final answer, the shift in perspective, viewing forces as the geometry of hidden dimensions, is arguably one of the most influential ideas of the 20th century.
It really is. Kaluza didn't just give us a theory, he gave us a new language. He taught us that when the world doesn't make sense in the dimensions we have, we might just need to look for the ones we're missing. He faced the sphinx of quantum theory and the inconsistencies pointed out by Einstein, and he still pushed forward with the belief that unity was possible. That drive for a single universal tensor is still the North Star for physicists today, even if the math has moved from 5 dimensions to 11 and beyond.
Kaluza's legacy is a blend of mathematical triumph and physical mystery. He showed that the dualistic nature of electricity and gravity could be reconciled if we were willing to expand our horizons, literally. It's a story of how a surprisingly courageous attack on a problem can change the course of history, even if the person who launched it remains a relatively obscure figure. We're still living in Kaluza's cylinder, trying to figure out if we can ever truly feel the curve of that 5th dimension.
The early 20th century was a golden age for physicists trying to build a single, unified theory of the universe. Most people know about Albert Einstein and Theodore Kaluza, but there's another figure, Hermann Weyl, who proposed a different path to unification. While Kaluza was adding a 5th dimension, Weyl looked at something more subtle, called gauge invariance. It was a failed theory at first, but it ended up becoming the literal blueprint for how we understand every single particle and force in the universe today.
It's a remarkable turnaround story. In 1918, Weyl published Gravitation und Elektrizität, or Gravitation and Electricity. He was a mathematician by trade, and he found Einstein's general relativity so beautiful that he wanted to push the geometry even further. Einstein had shown that gravity is just the curvature of space-time, essentially how the grid of the universe bends. Weyl's big idea was to ask, what if the ruler we use to measure distance also changes as you move through that grid?
That sounds like a nightmare for a carpenter, but in physics, why would you even want your ruler to change? What's the benefit of that kind of complexity? The early 20th century was a golden age for physicists trying to build a single, unified theory of the universe. Most people know about Albert Einstein and Theodore Kaluza, but there's another figure, Hermann Weyl, who proposed a different path to unification. While Kaluza was adding a fifth dimension, Weyl looked at something more subtle, called gauge invariance. It was a failed theory at first, but it ended up becoming the literal blueprint for how we understand every single particle and force in the universe today.
It's a remarkable turnaround story. In 1918, Weyl published Gravitation und Elektrizität, or Gravitation and Electricity. He was a mathematician by trade, and he found Einstein's general relativity so beautiful that he wanted to push the geometry even further. Einstein had shown that gravity is just the curvature of space-time, essentially how the grid of the universe bends. Weyl's big idea was to ask, what if the ruler we use to measure distance also changes as you move through that grid?
That sounds like a nightmare for a carpenter, but in physics, why would you even want your ruler to change? What's the benefit of that kind of complexity?
For Weyl, it was about consistency. He argued that if you can't compare the length of two vectors at different points without carrying one to the other, then the choice of scale or gauge at each point should be arbitrary. It's like saying, if you're in Paris,
That's
Weyl, he was in,
it was while most people, the early 20th century was a golden age for physicists trying to build a single, unified theory of the universe. Most people know about Albert Einstein and Theodore Kaluza, but there's another figure, Hermann Weyl, who proposed a different path to unification. While Kaluza was adding a fifth dimension, Weyl looked at something more subtle, called gauge invariance. It was a failed theory at first, but it ended up becoming the literal blueprint for how we understand every single particle and force in the universe today.
It's a remarkable turnaround story. In 1918, Weyl published Gravitation und Elektrizität, or Gravitation and Electricity. He was a mathematician by trade, and he found Einstein's general relativity so beautiful that he wanted to push the geometry even further. Einstein had shown that gravity is just the curvature of space-time, essentially how the grid of the universe bends. Weyl's big idea was to ask, what if the ruler we use to measure distance also changes as you move through that grid?
That sounds like a nightmare for a carpenter, but in physics, why would you even want your ruler to change? What's the benefit of that kind of complexity?
For Weyl, it was about consistency. He argued that if you can't compare the length of two vectors at different points without carrying one to the other, then the choice of scale or gauge at each point should be arbitrary. It's like saying, if you're in Paris and I'm in London, we should be able to choose our own units of measurement locally, and the fundamental laws of nature should still work out. When he did the math to make the laws of physics invariant under these local scale changes, a new mathematical field popped out, and that field looked exactly like the equations for electromagnetism.
So he tried to get electromagnetism for free just by demanding this freedom to change scales. It's an incredibly elegant thought, but I know Einstein wasn't exactly a fan. He famously shot it down with something called the second clock effect. Why was that such a deal breaker?
Einstein was always very grounded in physical reality. He pointed out that if Weyl was right, the history of an object would determine its size and its internal clock rate. If you took two identical clocks, kept one on Earth and sent the other on a long trip through an electromagnetic field, they wouldn't just be out of sync when they reunited, which actually happens in general relativity. They would be ticking at completely different speeds. Their physical gauge would have shifted. We'd see atoms emitting light at all sorts of random frequencies depending on where they'd been. Since we see sharp spectral lines from atoms everywhere in the universe, Einstein knew Weyl's specific physical interpretation had to be wrong.
So Weyl's theory dies right there in 1918, but we're talking about him today because it didn't stay dead. It underwent this bizarre reincarnation about a decade later. How did it transition from a failed theory of gravity to the foundation of quantum mechanics?
It's one of the great pivots in science. In 1929, after the quantum revolution, Weyl realized that the ruler that needs to be flexible isn't the physical length of a vector in space, but the phase of a quantum wave function. Think of a wave function like a little arrow spinning in a hidden internal space as a particle moves. In quantum mechanics, we only care about the square of that wave function to find the probability of where a particle is. Because of that, you can rotate that little arrow by any angle, change its phase, and the physical results don't change. That's a symmetry.
Okay, so if I rotate all the arrows in the whole universe by the same amount, nothing changes. That seems straightforward. But Whale took it a step further, didn't he? He went local again.
Exactly. He insisted on local gauge invariance. He said, why should the rotation of my wave function arrow in New York be tied to the rotation of an arrow on Mars? We should be able to rotate them independently at every single point in space and time. But if you try to do that with a standard quantum equation, the math breaks. The flow of the wave function gets messed up because the arrows are pointing in conflicting directions as you move from point to point.
So you have a broken equation. How do you fix it without giving up that local freedom?
You have to introduce a mediator. You add a new field to the equation that acts like a translator. It tells the wave function how to adjust its phase as it moves so that the physics stays consistent. And when Whale added this translator field to satisfy local gauge symmetry, it wasn't just some abstract math, it was precisely the electromagnetic field. The photon, the particle of light, is essentially the physical manifestation of nature's need to keep quantum phases consistent across space.
That is a profound shift in perspective. Instead of seeing light as just something that exists, we see it as a logical necessity born out of symmetry. But Whale was just working with electromagnetism. How did this become the blueprint for the entire Standard Model, including the nuclear forces?
That's where the story gets even bigger. In 1954, Chen-Ning Yang and Robert Mills took Weil's idea and applied it to more complex symmetries. While electromagnetism uses a simple circular symmetry called U1, where you're just rotating one arrow, the nuclear forces involve more complex rotations in internal spaces. For the weak nuclear force, you have a group called SU2, which involves 3 different force-carrying particles, the W and Z bosons. For the strong force that holds nuclei together, it's SU3, which gives us 8 gluons. These are all called Yang-Mills theories, but they are built directly on the foundation of Weil's gauge principle.
It's almost like a recipe. You pick a symmetry group, you demand it be local, and the universe hands you a set of force-carrying particles. But there's a catch, isn't there? If these particles come from pure gauge symmetry, they're supposed to be massless, like the photon. But the W and Z bosons are actually very heavy. Doesn't that break the whole logic?
It does, and for a long time, that was the big crisis. If the symmetry is perfect, the gauge bosons must be massless. If they have mass, you've destroyed the gauge invariance that made the theory work in the first place. This is why the Higgs mechanism was such a big deal. The Higgs field allows the symmetry to be spontaneously broken. It's like the symmetry is still there in the laws of physics, but it's hidden in the actual state of our universe. The W and Z bosons get their mass by dragging through the Higgs field, allowing us to keep the beautiful gauge structure Weil envisioned, while still matching the messy reality of massive particles.
It's fascinating how Weil's failed 1918 theory provided the exact mathematical tools needed for this. He was right about the importance of gauge, even if he was looking at the wrong part of the universe to apply it. But what about gravity? Weil started this journey trying to unify gravity and light. Does gauge theory actually help us with the one force that still won't fit into the Standard Model?
That is the million-dollar question. Mathematically, general relativity looks a lot like a gauge theory. Einstein's theory is built on diffeomorphism invariance, which is a fancy way of saying the laws of physics don't change regardless of how you label your coordinates in spacetime. In a sense, gravity is the gauge theory of spacetime itself. But when we try to quantize it using the same methods that worked for the other forces, the math blows up. We get infinities that we can't get rid of. Physicists are still struggling to find a gauge-like description of gravity that plays nice with quantum mechanics.
It's ironic. Weil's attempt to use geometry to explain light ended up giving us a non-geometric understanding of light, while the original geometric force, gravity, remains the odd one out. Is there any modern interest in going back to Weil's original 1918 ideas, the ones Einstein rejected?
Actually, yes. There's been a bit of a revival in Weil gravity or conformal gravity theories. Some physicists wonder if at extremely high energies, or in the very early universe, the scale invariance, while proposed, might actually be a real feature of nature. Some even argue that Einstein's second clock effect objection might be bypassed if you change how you define mass and length in those extreme environments. It's still speculative, but it shows that Weil's 1918 intuition about scale hasn't been completely discarded.
It's incredible that a paper written over a century ago, which was immediately called physically untenable by Einstein, still has researchers digging through its footnotes. It really underscores how powerful a deep mathematical symmetry can be.
Even if the first application is wrong, the underlying structure often points to something true.
Weil was driven by a belief in the inner harmony of mathematics and physics. He once famously said that if he had to choose between truth and beauty in his work, he would usually choose beauty. The irony is that by following that aesthetic sense toward gauge invariance, he stumbled onto a truth that was far more expansive than he could have imagined in 1918. He didn't just unify gravity and light, he provided the framework that eventually unified almost everything else.
So, looking at the big picture, if someone asks what the most important concept in modern physics is, gauge invariance has to be near the top of the list. It's the rule that says the way we describe things shouldn't change the things themselves. And from that one rule, we get the photon, the gluon, and the very structure of matter.
Exactly. It's the ultimate bookkeeping principle. It tells us that the universe has these hidden internal symmetries, and the forces of nature are just the messengers that keep those symmetries in check. Without gauge invariance, the quantum world would be a chaotic mess of inconsistent phases. With it, we have the standard model, the most precisely tested theory in human history.
It's a testament to Weil's legacy that we're still living in the world he sketched out, even if he had to be wrong first to get there. It makes you wonder what other failed theories today might be the blueprints for the next century of physics.
It's a reminder to keep an eye on the beautiful math, even when the physics isn't quite there yet. Weil's journey from a failed gravity theory to the consecrated principle of the standard model shows that in science, sometimes the most important ideas need a second act.
966. General Meeting of December 22nd, 1921. Communicated on December 8th on the unification problem in physics. From the 8 Kaluza. In Königsberg. Submitted by Mr. Einstein on December 8th, 1921. S. above, p. 859. In the general theory of relativity, in order to characterize world events, the fundamental metric tensor GNU of the four-dimensional world manifold, interpreted as the tensor potential of gravitation, must be introduced separately from the electromagnetic four-potential CE. The dualistic nature of gravitation and electricity still remaining here does not actually destroy the ensnaring beauty of either theory, but rather affords a new challenge towards their triumph through an entirely unified picture of the world. A few years ago, H. Weil 1 put forward a surprisingly courageous attack to the solution of these problems which belong among the most magnificent ideas of the human spirit. Through the radical re-examination of the geometric grounds he obtained, in addition to the tensor GNU, a kind of fundamental metric vector, and interpreted it as the electromagnetic potential key, there the complete world metric is claimed to be the common source of all the natural phenomena. Here we strive for the same goal in a different way. If we disregard the difficulty which is associated with the practical application of H. Weil's profound theory, it is thought to be quite idealistically possible to realize completely the unification idea, in which the gravitational and electromagnetic fields stem from a single universal tensor. I would now like to show that such an intimate combination of the two forces in the world appears to be possible in principle. The rotational form of the electromagnetic field components FKL, and also the apparent formal equivalence in the structure of the gravitational 1 and electromagnetic equations 2 lead us to the conjecture that FKL equal TO2. Zum Unitätsproblem der Physik, Sitzungsbe, Preus, Akkad, Wis, Berlin, Math. Phys, 1921, 966 to 972. Revised translation by V. T. Toth, based in part on translation by T. Mutter, HUPD 8401, March 1984. D. Per. Phys. Univ. Hiroshima. 1 Sitzungsbe. D. Burl, ACAD. 1918 p. 465. 2 in this respect refer to H. Thuring. Phys. ZTCR 19 p. 204. H. Kaluza, on the unification problem in physics. 967. 9 to 9a. X may somehow be equal to the truncated 3-index quan. Equal to x plus ini, 9ix. Provided there is a room for this tighties idea, one may be drawn with greater confidence to a path that previously seemed less attractive, since in a four-dimensional world, beyond the 3-index quantities used as the field components of gravitation, no further such quantities exist, such an interpretation of fxx is hardly supported unless one makes the otherwise extremely odd decision to ask for help from a new fifth dimension of the world. Although our rich physical experience obtained so far provides little suggestion to such an extra world parameter, we are certainly free to consider our space-time to be a four-dimensional part of ours. One then has to take into account the fact that we are only aware of the space-time variability of state parameters by making their derivatives with respect to the new parameter vanish, or by considering them to be small as they are of higher order. Cylinder condition. Misgivings about the retrogressive introduction of the fifth dimension are rendered groundless by connecting the world parameter to the three index quantities. We therefore enter into Rs and extend Einstein's ansatz to Rs. At the same time, we introduce the new parameter 2, in addition to the usual a 1 to 4. If the fundamental metric tensor of this Rs is expressed as gr2, the, denoted here by tact, become, by virtue of the three index quantities cylinder condition, IKL, as before, 210, 90 to 90, 2,100,000, 900, 2,100,000, 921 x 10 equal to 90 times plus 903 x 21 feet 000 inches 00. This result is at first sight hardly encouraging. Indeed, Fox appear in the form of a rotation, but the 10 IXO, which would have to be of electric nature according to our interpretation, are in danger of being in the way. Nevertheless, we further investigate the above result and, in order to keep. By indices divided by a comma is meant the differentiation with respect to the corresponding world parameter. Latin indices always run from 0 to 4 and Greek ones only from 1 to 4. 968. General Meeting of December 22, 1921. Communicated on December 8. Fox proportional to fx we set. 90 times stu, 100 times 900, equal to 20. So that the fundamental metric tensor of ours substantially becomes the gravitational tensor potential framed by the electromagnetic 4 potential. The role of the component g in the corner remains undetermined for the time being. Introducing the shorthand sigma for the sum qxa plus qx, corresponding to fxx we have. Gonal equal to Arol equal to Gilo Abilguk equal to Joko equal to 8%. Consequently, the electromagnetic field fxx, its associated field sigma, and the gradient of g use up the 35 new 3 index symbols, 5 of which vanish. Moreover, from the comprehensive equality, equal to tick plus key plus lick, m imic plus imkli plus imlick, arise the well-known relations by virtue of the cylinder condition. F plus fx equal to 0 and 9, x equal to 9, ax. We now restrict, as usual, the choice of parameters by g equal to 9r's equal to -1, and let gr differ only a little bit from the Euclidean value -8, approximation 1, with equal to index tensors, the intraseating components of the 2, 4, 0, a 0, 0 equal to 0, a 0, 0, 0 equal to d equal to 0. Fortunately, the associated field in EQ 3 does not participate here. Among electric quantities, only derivatives of the fields appear which determine the curvature of R's. Further, by making the contracted tensor, RIC, equal to IRRK, we find, according to our assumptions in the well-known notation, R equal to WWP as earlier, ROMU equal to RMUF RU, OG. Therefore, the 15 components of the curvature tensor on the left-hand side reduce into 1. The ordinary field equations of gravitation. 2. The basic. In the four-dimensional sense, at Kaluza, on the unification problem in physics. 969. Electromagnetic equations, and 3. A Poisson equation for the yet unexplained G. Therein lies the foremost justification of our ansatz, and the hope to consider gravitation and electricity as manifestations of a universal field. For the energy-momentum tensor of matter, dominating the right-hand side of the field equations in Rs, holds the following under approximation wine, tick equal to ho. U 40th rest density, U equal to dx ds ds 2 equal to gim dada. Since now, for all three types of field equations, rho top, it follows from the Maxwell equations that according to EQ. 6. For the components of the four-current, I equal to pot equal to top how equal to AA, po rest charge density, dx, do 2 equal to 9x dx dx. The space-time energy momentum tensor is thus framed essentially by the current density. We then continue further investigation under the assumption UO, U1, U2, U31, 1, approximation 2. This implies not only a small velocity but also a very tiny specific charge of moving matter. In fact, as thereupon no do 2, ES 2, it follows from EQ. 8, equal to 10 to 14, equal to 3.06x. First of all, this equation teaches us again that in this case, we need to understand the electric charge essentially as the fifth component of the energy momentum of the matter moving across the space, 2O, equal to const. A further merger of two formerly heterogeneous basic concepts thus appears, because finally 2, T11, T22, T33, 0 in approximation 2, we find according to EQ. 7, equal to G, according to the equation of motion, see the next section. 970 General Meeting of December 22, 1921, communicated on December 8. So that for the ordinary form of the field equation of the first kind, x rho equal to 44 rands equal to 10. The corner potential G is also proven, due to EQ, 6, to be essentially minus 9,442. The gravitational potential, while equal to keeps the former meaning. After we thus disposed of the standard quantities in the field equations in a satisfactory way, we still face with the question whether the geodesic equation of motion in RS, do, ds the first, 11, then represents the motion of charged matter in the gravitational and electromagnetic field in accord with experiments. In approximation 2, this is immediately the case, due to the interchangeability of ds and do 1 obtains according to EQ. 3, dido, equal to plus 2 af u to 0 times 2 11a, that is due to the smallness of the term with 0 2 for the force density 1 finds, equal to it plus f. I adapted, see footen. 12, the splits automatically into a gravitational and electromagnetic part of the ordinary form. Finally, for the 0 component of EQ, 11. There remains only equal to S4, equal to 2094, 4D, so that, in approximation 2, the quasi-static Dr. Poe, 11 billions, 2x94, 4 becomes. Small in higher orders, the necessary constancy of PO seems to be guaranteed. Accordingly, hence also for the equations of motion the associated field remains significant in our approximation. Cf. 8a, That Kaluza, on the unification problem in physics. 971. If approximation 2 was in accord with the reality, the unification theory under investigation would be executed, as mentioned earlier, substantially in a satisfactory manner. A unique potential tensor generates a universal field which splits, in ordinary condition, into a gravitational and electromagnetic part. Now, however, the matter at least in its smallest building blocks is not at all weakly charged. Following Weyl's expression, its macroscopic rest is confronted with its microscopic restlessness. And this holds, in the above-mentioned view, quite specifically for the new world parameter x0, for the R0 is not small, and so the velocity component U0 electron or H nucleus. U0 is not at all small. In the form constrained by approximation 2, the theory can, at best, coarsely describe macroscopic phenomena, and a fundamental problem arises concerning its very applicability to those elementary particles. If one now, nevertheless, tries to describe the motion of the electron by geodesics in 5 rands, one immediately meets with the serious difficulty one which threatens to destroy the foundation laid here. It lies simply in the fact that, with the rigid application of the previous assumptions, U0 for the electrons becomes enormously large owing to equal to 1.77 arc 107, reducedum in light seconds, so that the last term in EQ, LLA, instead of vanishing, assumes a value that exceeds everything and defies all experience, provided that everything remains formally as before. Now the larger value of U0 indeed implies modifications of the theory anyhow. The interchangeability of ds and sigma is lost, but it seems almost impossible to develop the theory only in the old framework without any new hypotheses. Nevertheless, with full reservations, I believe in finding, clearly in the following direction, a way which provides a fully satisfactory point of view leading to the goal. Since 000 rands, 44 rands even for arbitrary U0, provided that the velocity of the matter which generates fields is not too large. Two gravitational terms in EQ, LA, take opposite signs if the nature of x0, which has been completely irrelevant, is determined suitably. And it then seems that, apart from the gravitational constant kappa, which is slightly questionable anyhow, a reconciliation is possible between two compelling magnitudes for which gravitation is obtained as a kind of the difference effect. One is tempted to be bribed by this possibility with the prospect that the role of a statistical quantity may be assigned to that constant. At the moment, the consequence of this hypothesis is not yet examined sufficiently. Other. 1. I wish to thank Mr. Einstein for his valuable interest in the origin of the above assumptions and the suggestion of the inconsistencies described here. 972. General Meeting of December 22, 1921, communicated on December 8. Possibilities should also be searched for. After all, what threatens all the ansatz which demand universal validity is the sphinx of modern physics, quantum theory. In spite of full recognition of the aforementioned physical as well as epistemological difficulties piled up in front of our understanding developing here, it is rather difficult for us to believe that, in all those relations which in their formal unity seem hard to be replaced by anything else, only a capricious accident performs its alluring play. If it could be proven some day that there exists more behind the presumed relations than merely meaningless formalism, then this would certainly imply a new triumph for Einstein's general theory of relativity, whose appropriate application to the five-dimensional world comes into question.